In this presentation, I will provide an overview of the theoretical foundations of machine learning theory. This video is intended for a more mathematically inclined audience. So this is the outline. We will start off with why I made this tutorial, and then we'll dive into the actual content. We will, of course, state explicitly what the main problem is we're trying to solve, and then we'll do a series of relaxations to arrive at a feasible problem called empirical risk minimization. We will also talk about asymptotic and non-asymptotic analyses, and then we'll also explain the notion of probably approximately correct framework. And finally, I would wish to illustrate the theory using a particular PyTorch example. Here are some of the keywords of this talk. As you can see, probability theory is extremely important here. Okay, so why did I decide to make this video? A while ago, I came across this YouTube lecture from Vladimir Vapnik, the inventor of SVM, and this is the first few slides, actually the third slide of the lecture. When I first saw this slide, this was my reaction. I was completely overwhelmed and was determined to really understand what Professor Vapnik had to offer. Therefore, I embarked on a journey to understand more about statistical learning theory. So, inspired by Richard Feynman's way of thinking, I then realized the founding fathers of statistical learning theory pretty much did what Feynman did. That is, they wrote down the problem, thought very hard about the problem, and eventually the problem was solved. As an example, this is partly inspired by my lab members at NTU. This is a rough workflow of how my previous lab does research. The lab was called ADCSL, so I call this the ADCSL algorithm. The first step is usually writing down the problem in terms of clear, explicit mathematics, which is usually called problem formulation. Then after everything is specified, we would do group meetings and think really hard about the problem. And usually this doesn't really solve the problem, since the problems are usually non-convex to begin with. Therefore, relaxation methods are typically used, something like semi-definite relaxation. And these methods can sometimes be solved using simpler algorithms such as Dator's algorithm or ADMM. And then we hope and pray that by solving the new problem, the original problem was somewhat solved to a certain level. So it turns out that the same philosophy can also be used to understand statistical learning theory. The main problem we're trying to tackle is called risk minimization. And thanks to Professors Vapnik and Chervanenkis, they thought really hard about the problem and then kind of wrote down simpler versions of the problem called empirical risk minimization. And methods to solve this kind of problem were proposed, such as gradient descent. And basically, the idea is to use probability theory to analyze how far we are from the original problem, statistically. So let's start off with a simple example to illustrate the entire setting. Say we want to do weather forecast based on temperature and humidity of the environment. Let's first discuss the first probability space. Suppose we have a sample space X, and each element in this set is a vector containing the temperature and the humidity of the weather. We denote the probability of each outcome as Px of x. The second probability space has a sample space called Y, and it consists of two outcomes, rainy and sunny, with Py being the probability measure. So the idea is the following. Nature will first decide what x would be based on the P of x. Then God will play dice based on the conditional probability P of y given x to generate y. The main objective here is to find an f such that we can make good predictions about the weather given the temperature and the humidity. Which leads us to the first problem of interest, that is risk minimization. Here we are searching for a measurable function that yields the lowest expected loss with respect to the joint probability measure P sub xy. Some people might call this the Bayes predictor. The main issue with this problem is that we do not know what the probability measure is beforehand, and also searching in the space of all measurable functions is way too complicated. Therefore, let's relax this function set constraint and arrive at problem 2. We define a particular function class, which we will sometimes call a hypothesis set, let's say a particular CNN architecture, and we denote the optimal function here as fCNN star. Still, we don't know p sub xy, so this will have to be discussed later. Here we have a brief overview of the gap between the first two problems. This calligraphic fCNN denotes the set problem 2 is optimizing over. F star CNN is the optimal function within this set. And usually the F base is not going to be within this set, or at least there is going to exist some gap. If we measure the true risk of fCNN and the true risk of F base, some people might call this the approximation error. This brings us to the idea of the universal approximation theorems. Many researchers, such as Sabenko and Barron, have made the argument that neural networks are universal approximators, which implies that they can potentially approximate any function to arbitrary precision, at least in theory. So this is usually the point that these papers are trying to make. Now back to problem 2. We still don't know p sub xy. How do we deal with the objective function here? Is there something in probability theory that we can use? Well, this is where the law of large numbers comes in. Now, I should point out that technically, if we want to be rigorous, we should use the uniform law of large numbers. But since the idea of uniform convergence is a bit advanced here, I would just use the weak law of large numbers to roughly illustrate the idea. The weak law of large numbers states that for a given sequence of IID random variables x1 to xn, the sample mean will converge to the true mean in probability. So basically, by using this law, we can arrive at the feasible problem, that is empirical risk minimization. So essentially, we just replace the population mean with the empirical mean and minimize this one, which means that we need to collect a dataset of XY pairs, which we denote as D. And this is actually what we mean by training a neural network. But the law of large numbers only tells us something useful as n approaches infinity, which means the dataset has to be of an infinite size. But that's not really going to happen in real life, so can we still say something useful or insightful as n gets larger, rather than asserting that it has to go to infinity? And this is where non-asymptotic analyses could be potentially useful. So the inequality that we're trying to discuss here is called Hoeffding's inequality. It's a particular type of concentration inequality. So here's problems 2 and 3. And we know that from the law of large numbers, as n approaches infinity, the objective function of problem 3 converges to that of in problem 2 in probability. But how fast does it converge as n grows larger? Well, this is where Hoeffding's inequality comes in. Here is a simpler form. You can refer to this link right here. The original Hoeffding's inequality is usually written in this form, but the main takeaway is that as n grows larger, the probability of the sample mean deviating more than epsilon away from the population mean decays very quickly. So in this case, big data really matters. So the important thing is that as we have a larger and larger data set, our confidence that problem 3 is getting closer to problem 2 should roughly increase very quickly, assuming that we have IID samples. So this page briefly summarizes what we discussed. The main problem is to minimize the true risk over all measurable functions. But since the set of all measurable functions is too large, we will settle with a particular set of functions of our choice, which we will, for the sake of simplicity, we might call this a particular CNN set, or a particular CNN of a particular CNN architecture. And by using the sample mean instead of the true mean, we arrive at the ERM. And the gap here is usually called estimation error. The gap here is called approximation error. This page is just to explain certain ways to tighten the gaps between the problems, which briefly justifies the reason to use large neural networks and large datasets. However, it's still quite important to note that as we use larger and larger neural networks, we have a risk of enlarging this gap. And this is usually called overfitting, although I would note that in recent papers, there are there are papers that point out the potential benefits of using large models, such as those that are like LLMs, and the idea of overparameterization, double descent. But in this particular tutorial, we'll just focus on the classical theory. Now, I would like to point out that we will never know what the true risk is. We will only know the empirical risk. The question is, when we do empirical risk minimization, is it possible to state that the true risk will also have a high probability of being small? Well, this brings us back to the slide from the very beginning of this video. It turns out that if this function set, in this case FCNN, if this set has a finite VC dimension, which we will explain later in a different video, then it is possible to minimize this true risk using the empirical risk. And for now, we'll just view VC dimension as a measure of complexity of this function set. So let's state this more formally. The probably approximately correct framework, or PAC framework, can be stated as follows. If a function set has a finite VC dimension, then for any arbitrarily large probability, the true risk will be upper bounded by the empirical risk plus a function of the VC dimension. In other words, it is probably approximately correct to do ERM in the sense that we would probably also minimize the true risk by only focusing on the empirical risk. So this page is to summarize once again the PAC framework. If FCNN has a finite complexity or VC dimension, then with high probability, the true risk would be less than or equal to the empirical risk plus a function of the VC dimension, which means doing empirical risk minimization is probably approximately correct. Now I should note that the PAC learnability framework could be introduced more rigorously, and for that I would refer to the lectures of Professor Scheiben David. I really recommend those. So let's do a simple example. Here we use this particular public example from the PyTorch website. Now, I assume that the audience has at least some familiarity with Python and PyTorch. So here I'm just going to illustrate parts of the code which correspond to the framework that we previously mentioned. On this slide, it's quite clear that what we're trying to do is to prepare a dataset which corresponds to this section of the this part of the minimization problem. And here, when we define a particular class in PyTorch, this corresponds to a particular function class or hypothesis set that we previously mentioned. This specification determines the complexity of the hypothesis set or the VC dimension of the function set. Now, when we go into the for loop of the data loader for training, we are essentially doing empirical risk minimization. We're minimizing this, essentially. And the algorithm we typically use is a gradient-based approach, such as stochastic gradient descent. And when we evaluate the test error, we are essentially having a rough idea of whether or not the PAC framework is valid. Now, I should point out that the test error here is still not the true risk. We will never know the true risk, but at least this is a step in that direction. But the point is, doing this, we kind of have some confidence that our neural network training was probably approximately correct. So to conclude, in this talk we explain how to state what we want explicitly and mathematically, and briefly explain the choice of the neural network, which makes sense at least in theory, and why we typically use the ID assumption when we discuss the theoretical aspects of machine learning theory. Now I should note that in practice people usually use small batch sizes, and typically the data is not IID, which means the law of large numbers, and all the previously mentioned theory doesn't entirely reflect what we see in practice. However, this is at least the first attempts these researchers did in hopes to develop a rigorous mathematical theory for learning. So understanding the core arguments and the style of logical deduction is, in my opinion, more important here. But anyway, we can still kind of view stochastic gradient descent as at least trying or attempting to minimize the empirical risk. But that is also not guaranteed because the whole problem is non-convex and very complicated. And in the next talk, I think I will also discuss a little bit more about what uniform law of large numbers is. I previously mentioned this and kind of said that we'll discuss this later. And also we'll consider explaining some ideas called Rademacher complexity and other more modern generalization bounds. So here are some of the key references. If there are any other references that I've missed, I would link them later in the description. And with that, I think I'll end here. Thank you very much for listening.